Okay, so let us get started here. So last lecture we were talking about recurrences and how recurrences can be solved. So in particular, we were talking about uh, homogeneous homogeneous linear recurrences, where you have equations of the form f of n equals f of n minus 1 plus f of n minus 2 and so on, right? So the general form of uh, the recurrence is like this: f of n equals uh, some summation of f of n minus i's for different i's. And we start from the knowledge that these sorts of equations have solutions of the form x to the power n for some x, and then we substitute that into the solution, into the equation, and then do some algebraic simplification, and that'll yield essentially a polynomial equation on this variable x, and then we can solve that polynomial. And then, of course, we only know how to solve quadratic equations, so we cannot use this for other types of equations. But that's not a general limitation. It's just that we in this class don't know how to do anything beyond quadratic equations. But otherwise, the technique is general enough, and it can be applied. And once you find the solution, then once you find these roots of this equation, or this polynomial, then you write down that the general form of the solution is like this. So essentially, you are basically saying that it's for each root, there is we are solving for the solution. We were solving for x to the power n, and so we got many roots r1 through rd. And what we are going to do is we are going to say that the solution is of the form k1 times r1 power n plus k2 times r2 to the power n up to kd times r to the rd to the power n, right? So essentially, there is we suppose that there is some constant in front of each of those terms, and then we take the sum of those terms, and that is the general form of the solution. And then we can solve for k1 through kd by knowing what is the actual value for the first few terms, right? So in the case of Fibonacci, we substitute the known Fibonacci values for n equal to 0 and 1, and then we arrive at the solution that you know we arrive at the solution that it's of the form that the solution to the Fibonacci equation is of the form k1 times 1 plus square root of 5 divided by 2 whole to the power n plus this, where k1 is 1 by square root 5 and k2 is minus 1 by square root 5. Okay, so that's sort of what we did. So can I see a few more of you now? Okay, so there certainly should be more of you in the class. Okay, very good. So we talked about how to solve one type of recurrences, Uh, that's not the only type of recurrence that we will come across. So what we are going to do today is to discuss another form of recurrences, and discuss how to solve them, right? So before we do that, it's useful to talk about asymptotic complexity, which is a concept that comes up in algorithms, right? So the basic idea is that when we are talking about the runtime of the towers of Hanoi problem, we were reducing the runtime in a sense to the number of steps involved, right? So if you think about a program, the program has many steps, and each step may have many operations. And we could once again count the number of steps taken by the program, but then we are not entirely sure how much time each of those steps will take, right? So sometimes, there may be some operations that take much longer than other operations. So for instance, a division operation may take significantly longer than, let's say, an addition operation. And so when we count the number of steps, we are necessarily making a simplification in terms of how uh, we are calculating the runtime. And the reality is that we can't quite do a very accurate job, because not only do these operations, their speeds differ, and we can't possibly calculate each one of them accurately. The fact is that these differences are going to be different depending on the machine on which you're running these programs, right? So if you're running it on your phone, maybe it takes a certain amount of time. When you run it on your PC, then maybe it takes a somewhat different amount of time. So the notion of asymptotic complexity has been developed in order to sort of give a rough idea of uh, you know how long algorithms can take to run, without necessarily getting bogged down in all these details about how long do specific steps take on specific machines. Okay, so in particular for algorithms, one of the properties that we care about the most is how the runtime changes when you give it larger and larger inputs, right? So we are primarily concerned about the growth rate, right? So how fast does the runtime increase with the size of the input? Okay, so this notion is called asymptotic complexity. And so what we are going to do is we are going to calculate asymptotic complexity by leaving out the constants and sort of worrying only about the rate at which this function increases. Okay, so let's give the definition here. So um, one of the concepts in asymptotic complexity is what is called the big O notation, right? So the big O notation captures the rate of growth of functions. Okay, so we say, given two functions f and g, we can say that they have the same order, or f is order of g, which basically says that they kind of grow at the same rate. Okay, so the mathematical definition is that f of x divided by g of x stays within a constant factor. Okay, so here is an chart that shows two functions. One is a linear function, which basically grows linearly with n, which is the x-axis here, right? So we are plotting f of n on this chart, and n on the x-axis, right? So the f of n is the y-axis. So this is a linearly growing function, whereas this is here is a function that grows quadratically. And then you can see that as n increases, this function that grows quadratically, it increases much faster than the function that uh, you know grows linearly. And if you look at compare this, right? So if you do, what is the limit of let's just do, okay. So let us take, right? So this is, right? So this is a case where the n square function is growing much faster than the n function. So the ratio of their values will basically uh, increase more and more as you increase n, right? On the other hand, if you have um, if you compare these two functions, obviously the n square will cancel out and it is just 2, right? So 2n square and n square grow. We say that they have the same order, or we would say n, you know, 2n square equals order of n square, to say the fact that the rate at which uh, the they both grow at the same rate. Okay, so a simple way to think about this growth is to say, hey, I'm basically not going to worry too much about the constant factors involved, right? And I'm only going to worry about the uh, highest degree of the function, right? And I'm going to ignore the constants, right? So this is how you can think about the big O notation in an intuitive way. So for instance, you can say 10n, well, I don't have to worry about the constant, so I would say that it is order of n. So if I have 0.0001 n cube plus n, then I would say, once in this case, you would say that, okay, so this n cube is the higher degree term. So I can kind of ignore the lower degree term, and then I'm going to ignore the constant. So I'm going to say this is order of n cube. Okay, same way here, you can say that 10 to the power n grows much faster than 2 to the power n, which grows much faster than n square. So all these other terms will not dominate. The growth will be dominated by 10 to the power n. And so it is order of 10 to the power n, right? So if you follow this definition of limits and find the limit, of course, in each of these cases, you will find that the simplification that we have done is correct with respect to that definition. But in terms of working in practice, the way we go about doing this is basically by dropping all except the highest degree term, and then ignoring the constants. So when you compare terms like this, one is n times log n, and the other one is n. So clearly n times log n is n multiplied by some increasing function of n, right? So log n, although it grows relatively slowly as compared to n, it is still an increasing function. So n multiplied by log n will grow faster than just n. And so once again, we can eliminate this and the constant factor, and then we can say order of n log n, right? So when you have products like n log n, you cannot just say, hey, n is more important than log n. So you can ignore lower degree terms only when you're talking about sums of terms, right? So it's not that if you say x cube, let me just use n again, right? So you can't say n cube times n. I will just keep the n cube and not the n here, right? So when we say maintain, just keep the leading term, what we are saying is that when you have a sum of terms, then in the sum, then you can just retain the term with the highest degree. Okay, so that's what big O notation is. And when you uh, uh, do, in many of the other courses that you will take, you will come across this big O notation, and you will learn about it in more depth in your algorithms course that you'll take in yeah, probably next year. Okay. But for now, the reason why I'm introducing this is partly because, of course, you're going to come across it again and again. And part of the reason is because the when we solve recurrences, when we make these simplifications in terms of dropping constants and not worrying about the highest degree terms, then that makes it easier for us to solve those recurrences. So the big O notation and the way we are going to solve the next class of recurrences, they go hand in hand. And that's why we introduce this big O notation at this point. Okay. So now we are talking about a different type of recurrence, right? So in the linear recurrence case, we had things of the form f of n equals f of n minus k, right? So in here, we have equations of the form f of n equals f of n divided by k, right? So that is the form that we are going to see today. And that class of recurrences occurs in a certain type of algorithms called divide and conquer algorithms, right? So the way a divide and conquer algorithm works is that you take the input, you divide it into pieces. Often these pieces are, if your input is n, often the pieces are n by 2 and n by 2. But there are cases where you divide it not into two pieces, but into k pieces, right? Or in this case, b pieces, right? And then each piece is of the size n divided by b, right? So then we apply the same algorithm recursively on each of the b parts, right? So we take, so we are trying to apply some algorithm A, and then we are dividing the input into several parts. And on each of those parts, we are going to apply the same algorithm, right? And in turn, when you apply the algorithm on this part, it'll get divided into smaller pieces and so on, right? And we will see examples of this in the next few lectures. So you don't have to really necessarily fully understand what a divide and conquer algorithm is, beyond the fact that these recurrences where on the right-hand side, instead of having n minus k, you have n divided by k, right? So those types of recurrences occur in the context of divide and conquer algorithms. And we have a very simple way of solving them, because there is this handy theorem called the master theorem, which basically tells us here is the solution to recurrences of this form. Okay. So it basically, there are, the solution may be one of these three. And the critical factor here is the relationship between A, B, and D here. Okay. So, so if D is greater than log of A with respect to base B, then the solution of this recurrence is O of n to the power d, right? So you can see that now here that we are not saying it is, n to the power d, right? Or that k times n to the power d for some constant, but instead we are just saying O of n to the power d, right? So in fact, the actual solution could be, k1 times n to the power d plus k2 times, n to the power, d minus 2, and so on. Okay. But from the order perspective, all that matters is the leading term. So by focusing on this asymptotic complexity, we can simplify the equation and the form of the solution. Okay. So if d is greater than this number, then the solution is O of n to the power d. If d is equal to this logarithm, then the answer is n to the power d log n. And if d is less than this logarithm, then the solution is of this form. Okay, so the proof of this theorem is fairly easy to show, but I'm not going to go into that at this point. It's enough to, even if you can prove it, it's not like you're going to use the proof in order to solve any recurrence. So what I want to do now is to explain the master theorem using or illustrate it using examples rather than trying to prove it, right? So the proof is not particularly hard, and when you take your algorithm course, you will go through the proof of this master theorem. So let's take some examples, right? So let's say you have a recurrence of the form T of n equals 2 times T of n by 2 plus n, right? So this kind of recurrence occurs very often in many sorting algorithms. Okay, so when you heard of algorithms for sorting lists of numbers or lists of anything, and there are various algorithms like that you may have heard of, like quick sort and merge sort and so on. So many of these sorting algorithms uh, are of this divide and conquer type, and they have their complexity uh, can be leads. So when you're trying to analyze their complexity, you often get this particular recurrence. And we can substitute, we can use the master theorem to figure it out, right? So we have to match this given recurrence with the general form, right? So, and then find what is A, what is B, and what is D, right? So what is A here?
2.
And B?
2.
And D?
1.
Right. So now that we have A, B, and D, we can check which of these conditions holds, right? So log, so let's compute log of A with respect to the base B. What is that in this case?
Also 1.
So A and B are the same, of course. Therefore, B to the power 1 equals A. So we have D equal to 1, log A equals 1. So we have a situation that corresponds to this case. So the solution is O of n to the power D log n, which we know that D equal to 1. So this is basically O of n log n, right? So most sorting algorithms have this complexity, right? So they grow somewhat faster than linear with the input, right? So so let's take another recurrence, right? Again, they are all going to look roughly the same kind because they are all of this standard form, right? So once again, can you tell me what is A, B, D, and log of A with respect to base B? Well, you can answer, right? What is A here?
Um, A is 4.
Okay, B,
2,
right. And D is,
3.
okay, and what is log A to the base B?
I don't know.
Well, what power of B will give you A?
2.
So, so that is 2. So now we have these two quantities, and then we can immediately say that d is greater than the log, right? So therefore, the solution is O of n to the power 3. Okay. So one of the things is that these recurrences are simple enough that if you apply the plug and chug technique that we talked about first, right, you will actually be able to uh, uh, prove get the answer in some of the cases, right? In other cases, like here, it will be a little bit more difficult, but not far from, you know, it's certainly within what you can do by using plug and chug. It just takes time, right? So you're you know to to use the plug and chug method, you probably take 15 minutes to solve the problem, whereas if you are just applying this master theorem, it'll take you half a minute or 1 minute. Okay. And then let's look at the last example. T of n equals 3 times t of n by 2 plus n. So we can once again write a is 3, b is 2, and d equals 1, right? So what is log b to a? Obviously, we don't have to know the exact value, right? Because we just need to be able to answer this question, right? So is d greater than log b to a or not?
It will not. Log of a base b will be greater than 1.
So this one is going to be 1 point, something, right? So let's say 1.5 or something like that. And so d is 1. So the case that we have is the third one, right? Conveniently, because it's the third, the we already looked at the other two cases, so we must be left with only this case, right? So the answer is O of n to the power log b to a, which is O of n to the power log 2 to 3. Okay, so um, that's the solution to this recurrence. Okay, any questions? So that brings us to the conclusion of the discussion on solving recurrences, right? So we talked about three approaches: the plug and chug technique, the second technique, which is applicable to linear recurrences, and then the third technique, the master theorem for solving uh, divide and conquer type recurrences, right? So uh, that gives you uh, you know uh, a range of techniques for solving recurrences, and by and large, you should be able to deal with most recurrences you are likely to come across using these three techniques. Okay, and then of course, the plug and chug technique, as I told you, is a very general technique, and there is really nothing that cannot be solved using the plug and chug technique, provided you have enough time, right? And if you're willing to spend time, then it can solve anything. Okay, so any other questions? So, by the way, for the next midterm, we are trying to do it without using lockdown browser. Instead, just each of you being on Zoom session, right? So just like the class, right? Except that we are going to do this in smaller sections, like your recitation, okay? And obviously during the exam, you have to keep the video and audio on at all times, right? So otherwise it's going to be a problem, right? So you can't just like during the lockdown browser exam, uh, we want to make sure that your video and audio is turned on at all the time. The same exact conditions will apply here. And and we also, you're going to, for the most part, if not entirely, the exam will be on paper, right? So you will write your answer on paper, and then at the end of the exam you will scan it, just like you used to submit your homeworks before, right? But all of that has to be done while you are on the Zoom session, and the TAs and I can see all of you, right? And we will keep, you have to keep the audio on, and we will keep the audio on, so that if there is something that you're doing that we don't quite understand, we can talk to you and fix the problem, right? So hopefully that would be a less stressful situation than the lockdown browser. And also it gives you a little bit more, uh, um, you know, it gives you more options in terms of proofs and pictures and whatnot, right? So those are easier to do when you write out by hand. Any questions about the exam, or anything else we discussed today or in the previous lectures? You're almost there, right? How many more lectures? Are you counting? No. Okay, I'm counting. There
Is
are
it
five more, right? So excluding today, there are five more, but one of them is going to be a midterm. So you have only 4 more lectures once you finish today, right? So you're almost there, right? One semester, and then, another 7 more, and you'll have your degree, right? Time flies. Okay, good. So let's go on to the next unit. Oh, no. Okay, so let's. Having a little bit of trouble. Okay, so for the pretty much the most of the remaining lectures, uh, we will be talking about um, recursion and functional programming, right? So this is sort of the last topic that we are going to cover, and um, it's a chance to get introduced to recursion, which is something that you're going to come across, throughout your career, right? So we are going to uh, learn recursion using what is called a functional programming language. And the reason why we do that is because we learn a lot of math in this course, and a functional programming language, uh, the programs kind of look like the functions that we define in this class, right? So we often write a recurrence. So a recurrence is a function. We write an equation for Fibonacci that looks like a function. We learn about functions and relations. So all of that is going to fit very neatly into a functional programming language. So notationally, you are sort of looking at a language that is going to be uh, quite familiar to you based on what we have done in the course so far, right? And the second reason why we do functional programming is because recursion is very natural in these languages, and it allows you to sort of think about uh, programming from a recursion first perspective, right? Because many times what happens is that uh, people are introduced to programming through languages where recursion is somewhat forced, or it's not the most natural thing to do. And what uh, the result is that it impedes people's ability to learn recursion, which is a lot more general than all of the other programming techniques that you may have learned so far, right? Again, some of you may not have learned any programming, just perfectly fine. And in fact, it's probably better, because then you don't have to unlearn some of the things that you have learned and relearn things in a sort of in a recursive, in a recursion first sort of approach. Okay, so that's what we are going to do. So So programs in this language are going to consist of a set of functions, much the same way that we have defined and used functions in a math class or in this class, right? So functions are the functions that we know from math. And again, if you are done some programming, many of you may have done some programming with Java, and of course you're familiar with the notion of variables in there. So variables in functional languages are not quite like that, right? They are much more like variables in algebra, right? So when we say f of x equals, x square, uh, this is not quite the same way we think of variables in Java, where we think about, okay, there's a variable is stored in memory, and it has a certain value. You can assign some value to it at some point, and then later on you can assign a different value to it and so on. That's not the notion of variables in math, right? In math and in algebra, variables are simply placeholders, right? So they represent uh, places where some values are going to be substituted, right? And this, you know, it, this notion is most clear when we talk about when we talked about quantification and predicate logic, right? So we have variables as placeholders, and then we talk about for all possible values of this placeholder, and for all there exists a possible value for this placeholder, and so on. And it is that notion of variable that we will be dealing with in a functional language. Okay. As an aside, uh, languages in which you think of variables as something that is stored in memory, and their values can be changed over time through assignments. uh, those languages are, we talk about them as languages where computation happens through what we call as side effects. Okay. Whereas in a functional language, one term that you will hear repeatedly is that there are no side effects. Okay. So you don't necessarily have to understand what exactly this means at this point, but I just want you to be aware of this terminology in case you come across it, or someone tells you, hey, what about side effects? You have some idea what that term might mean. Okay. And in a functional language, the data structures are going to be based on sets and operations on sets that we have discussed before, such as Cartesian products and so on. Okay. So the particular language we are going to use is called, standard ML. And a little bit of history: the term ML stands for meta language, right? So it was a language that was developed largely in the 80s. Okay, so uh, the idea was that it was a language, a very high level language for that makes it easy to program certain types of applications, in particular writing systems for proving theorems, right? So automatic theorem provers. And over time, because these theorem provers are nothing but programs, right? So a language for writing these theorem provers ends up being, simply another programming language, right? And that's how standard ML came about. And then standard ML was, developed largely in the late 80s and early 90s. And then there was another dialect called CAML, which stands for Categorical Abstract Metal. Well, I don't even remember the expansion anymore, right? So I think it's something to do with categorical abstract machine and ML. So they I guess they somehow merged those two phrases into CAML. So CAML is kind of like SML in many ways, but it has a few additional features for that makes sort of uh, more conventional programming a little bit easier. And also because the system was developed somewhat later in late 90s and early 2000s, it is a language that is more robust and is somewhat faster and so on. Okay, but the notation is a little bit takes you farther away from math, and so we are going to really be sticking with standard ML because the syntax is so much simpler. Okay, so has anybody heard of this language called Scala? Okay, yeah, Scala is so the developer of Camel then decided at some point that they want to do something like Camel in the context of Java, and Scala was born as somehow a way to do functional programming with sort of like Java syntax. Okay, so so in order to so we are going to be understanding how to write some programs and also be writing a few small programs, and that of course means that you need to be able to install this standard ML system on your machine. So if you really don't want to install, then there is also a website that allows you to directly type in these ML programs. So let's why is it not going there? Is that a problem? Okay. Right. So it gives you a console like this, and so here is, I guess I cannot draw with my pen on this application, but you can see that there is a program on the left, right? So there is a factorial function that's being defined. And then there is a second function called aux, which I don't quite know what it does. I guess it's just a example function, which calls factorial, and then it kind of prints it out. So let's run it. So here is the execute button. If I execute it, then it basically what it is doing is it's printing factorial for a number of values. And at some point, it's complaining that the numbers become too large. So here is so it's saying that uncaught exception overflow, which basically happens when it takes 12 factorial, and then when it multiplies that by 13, the number is too large to fit in in an integer variable, and so it leads to some error. But that's not really important for you. All that's important is here is a way of typing in programs, and let's see if I do aux1. Let's see what we get. So we didn't get a different result. But let's say instead we don't call this aux function, we simply call factorial, right? Factorial. Then execute. And so we just call factorial of 5, and we get 120. Okay, so let's go back to, so if you really don't like to install something, then you can work with this browser-based version of the standard ML system, but I really won't recommend it because it's not a very good system, and you'll find that once you start using it, you'll find that it's somewhat of a pain as compared to having a local installation, right? So, so how many of you run Linux? Not that many, huh? Okay, so as programmers, you're going to be doing a lot of Linux, either directly or indirectly, right? So pretty much all development happens on Linux. So if you don't know Linux now, then you will know soon enough, right? So if you have a Mac, then you can again install standard ML on a Mac. So if you look at this website, it'll tell you exactly how to install on your Mac. You can also install on Windows, which is actually easier because on Windows these days, right? Windows gives you pretty much a Linux machine. So, so what you should do is you should install what is called a Linux subsystem for Windows. And if you install it, then basically you will have a Linux machine run on top of your Windows, and you can use any Linux application. And then you can install SML on Linux by running this command from the command line. Okay, so again, if you don't know how to do this, you will learn. It's actually quite easy to do, and so yeah, so whichever way you go, you can install. And again, if you have too much trouble, then you can always stick to the browser-based version. It's not that we aren't going to do anything so complex that you cannot manage with this browser version. But again, I'll definitely recommend that you try installing it directly and using it directly on your machine. Okay. So, right. So, yeah, so this WSL is something that I would, strongly recommend. Those of you using Windows, if you don't have it already, you should have installed it a while ago, right? Because it's really a very good system. And it's something that, so again, Linux is where most software that you want is going to be on Linux, right? And so that's why you should be running Linux for most things that you do. Okay, so before you come back for the next lecture, I want you to have tried installing this, and you should have tried running something small on SML, right? Like some of the examples that I'm going to show today. You should have tried to enter them on SML and try to do it yourself. It's the whole thing is not going to take you more than half an hour to do, right? So so it's something that's going to take only a short amount of time, but you should do it because when you do it yourself, then you're going to understand it in a way that listening to a lecture is simply not going to get there, right? And if you understand it uh, by doing it yourself, then it'll be a lot easier to follow the lecture next time. Okay, so once again, all the links that you need are here, and so you can look at that uh, uh, and follow. So once you install Linux, you can run Linux by simply typing in SML on the shell window, and it'll tell you, it'll prompt you with a single minus symbol, just like what did we see there? Let's see what it shows you. I guess this one doesn't show any prompt, but if you have a shell window, it'll show you a prompt which consists of just a single, minus symbol. Okay, so I let's see how we are doing on time. Okay, so I'm not going to go into the command line and show you how these things look like today because we have only 20 minutes, and switching around from my iPad to my computer and back will take some time that I would rather not spend today, but we will do that in the next lecture. Okay, so once again, you have to run SML. I recommend that you run this command rlwrap SML, which allows you to sort of makes it easier for you to go back and correct your mistakes. Okay, so so you can type your programs on the console, or you can store your programs in a file, and then you can tell standard ML to if you type in this command, then it's going to read the file ABC, and it's going to read that program, any program that you have written, that you have stored inside ABC. Okay, so so while trying something out, you might find the command line, just entering the program directly. You may find that helpful, but once you have written the code, it's obviously easier to just store it in a file and use it later on. So let's slowly let's introduce SML to here. So in standard ML, at the top level, you type what are called expressions. Okay, the expressions can be often consist of calls to functions, but to start with, we will take simpler expressions that simply consist of things like arithmetic operators. So if you type in 2 times 3 semicolon, then you are telling standard ML to compute that value, right? So, and then it's going to print this for you, right? So it's going to say 2 times 3. Okay, it's the result is 6. But in addition, it prints a bunch of things. So what does this mean? It says that the result is a value, and it's always going to store every value in a variable, right? And it has a specially named variable called it, right? Or you can say it. So it is going to store the last thing that you evaluated. Okay, so so it's saying that the last thing I evaluated was yielded a value 6, and it is of integer type. Okay, so that's what this this whole thing says, right? So 2 times 3 is a value, and the value is 6, and it is a integer type value. Okay, so SML expects all inputs to be to end with a semicolon, right? It's not expecting every line to end with a semicolon, but when you finish doing something and you expect standard ML to give you a response, then you should have put a semicolon there because that's what tells standard ML that you finished saying what you wanted to say and you are expecting a response from SML. Okay. So sometimes SML, instead of printing the answer, it'll print an equal to sign. Okay, what that means is that uh, SML thinks that the whatever you are typing is not done. It's expecting more, uh, you know, to be typed in because it thinks it's not a complete expression. So, for instance, if you do 2 times and you put a semicolon and enter, then it'll say, hey, it'll either tell you that there is an error because the semicolon shouldn't appear there. But let's say you put 2 times and then you enter, right? So now, the SML system gets this input 2 times and then it knows, okay, I'm expecting, one more operand before this can be evaluated. So it's going to type an equal to sign, which is an indication to you that it is expecting more input, right? And then on the next line, if you type 3 and then a semicolon and then enter, then it'll again produce the same response, val IT6. Okay, so there will be times when it is expecting more input. You don't know what is left. So that's what I call as a state of confusion. And if you type Control C at that point, then standard ML will, drop whatever it is doing and come back to the top level prompt. So then you can type something from scratch, right? So so that's basically how you interact with standard ML at the top level. So here are a few more expressions. So for instance, 2 plus 3 times 4, and it's going to evaluate it. So 3 times 4 is 12, plus 2, 14. So not a surprise that it prints 14. Uh, so here is SML does have some quirks. So unary minus is not a minus. It needs to be a tilde symbol, right? So that's you know again you will see some of these quirks from time to time because of other design, the way the language is designed. There are some constraints some constraints plus the fact that it was a language that was designed in the 80s, not today, right? So those make for a few oddities like this. So there are going to be times when you are going to get error messages, right? So when you say 2 plus 2.2, okay, so it gives you this long error message. The often when you learn a new language, the biggest challenge is understanding these error messages, which often are very long, right? So what it is basically saying is that you are trying to add an integer with a floating point number. Okay, so that's what it doesn't like. It doesn't like an integer to be mixed with a real number, and it has a rather messy way of telling you that it doesn't like what it sees. So if you it's happy to add 2 real numbers, it's happy to add 2 integers, but it doesn't want you to mix integers with reals because it considers that to be an error, a programming error, and that's why it complains. Okay. Fortunately, this particular error is something that you're probably not going to see much of because pretty much everything that we will do will be with integers and not real numbers. On the other hand, right, so obviously, anytime you write more than one line of code, you're going to have errors. And so you're going to have to deal with some of these errors and try to interpret them, right? Sometimes you can make sense of the error, sometimes you cannot. So you just have to try something else, hoping that, this time you won't run into the same error. So far we typed in a few expressions. So let's catalog some of the operators. So there is addition, subtraction, and multiplication. These three operators can be used on integers as well as real numbers. True and false are Boolean constants. And for division, there are two different operators. For integers, you use an operator called div. And for real numbers, real number division is using the slash operator. Okay. And your Boolean and or not or have this form in standard ML. Okay. So most of this is just for reference, right? So I'm not, when you start writing something, then you can refer to these tables to see what the operators are, right? So standard ML also has a string type, right? So strings are going to be enclosed in double quotes. So you can just say, oh, by the way, okay, I'm sorry. So I missed the bigger point. So far, you are typing in just expressions. Here, you are essentially giving a name to some of these values, right? So the way you do that is you say, I'm defining a value, and the value, the name that I want to associate with the value is this, and this is the expression. This is the actual value. So we refer to this again as a variable in standard ML. And all of these are value definitions as opposed to function definitions that we will see in a little while. Okay. So here is a simple statement that says, okay, I'm setting a variable x to value 1. This is a variable y being set to value x plus 1 and so on. And one thing to remember is that although I'm using the same name here and here, right, it's not don't think of them as the same. If you use the same name in Java, then that means something. Here, these are actually two different variables. And basically, the moment you define this, essentially SML doesn't even know that you did that at some point. It completely forgets it, right? So you can reuse the name. Whenever you reuse a name, it's just going to forget the previous use of the name. Okay. So here is a string variable. And as I said, strings are enclosed in these double quote characters, right? And every time you type something in, SML sort of says, hey, I understand, right? So it's basically typing this back and telling you that, it's a value X, its value is 1. And whenever ML is going to print something back, it's also going to tell you what the type is, right? So you didn't say what is the type of X. So ML tells you that its type is integer, right? So once again, if for those of you who have done some programming in Java, one of the things you do is that you have to define the type of every variable before you use it. In standard ML, the variables are like variables in math, and in math you don't say what is the type of a variable, right? And so you basically use the variable, and SML will figure out what its type is. If it needs to know the type, it'll be able to figure it out by itself. Okay. And of course, sometimes when it can't figure out, right? So the reason why this error is so complicated is also partly because it's trying to figure out. And when you have a mixed mode expression that contains both integers and real numbers, it doesn't quite know what you intend. And that's why it's telling you something complicated.
Professor, could you
Yeah.
just explain again why for x equals x plus 1, it evaluates to 3?
I think it's just wrong. So I must have updated it at some point, and when I updated it, is possible that I updated something on this side without correspondingly updating on the right hand side, right? So you're right. So this should be 2. Okay, so you have the previous value of x is x equal to 1. So if you say x equal to x plus 1, you should get 2. Okay, so thanks for noticing. So this is for simple values. You can define functions in the same way. So the only difference is that you put this keyword fun instead of val, right? So fun f of x equal to 1. Well, that's a function that always returns a value 1. It basically ignores the parameter that you provide here and always returns 1. Okay, and it's going to tell you, hey, this is so for SML, for standard ML, it doesn't internally make a distinction between values like integers and functions. So it thinks of all of them as values. But when we write the code, we say fun when we are defining functions and val when we are defining values. Okay, but internally it thinks of everything as a value, and it's going to say value, the name of the function, and it says it is a function type. Okay, so that's what this means. It's a function type, and it's a function that takes anything and returns an integer, right? So remember, in when we talked about functions in this course, we say function from a domain A to codomain B is something we write down this way, right? F colon A to B. And it's pretty much the same notation that standard ML uses to represent this function, right? It says, the only difference is that it says because you completely ignore x, x can be anything, right? So that's why it uses this, what that stands for is any type. Okay, so it says that the input can be any type, the output is an integer. Okay, similarly, if g of x equal to x, then it says, okay, g is another function and the input can be anything, but it knows that the output is going to be the same thing. So it's basically saying this is a function that goes from some domain A to itself, right? So that's what it is saying. Okay, so so when it says int, it's referring to a specific type. When it says single quote and something, that's a way of saying that it can be any type. Okay, so so here is an increment function which takes some argument and returns 1 plus that argument. And once again, it says, okay, inc is a function which goes from integer to integer. Okay, and here is a max function. Okay, and max is also something that goes that takes 2 integers and returns an integer, right? So we talk about functions that take right. So we have seen functions that take multiple arguments. We write them down as f takes a times b to c, and once again it's the same notation it uses. Instead of the x, it uses a star, right? Just like in most programming languages, multiplication is denoted as star. So sticking to that convention, it's just the Cartesian product that we use in when defining functions is denoted using star in standard ML. Okay, so one other thing that's going on here is that the max uses an if then else function, which has the natural semantics that you would guess. If x is less than y, then the value of the function is y. If x is not less than y, then the value of the function will be x, right? So if you read it that way, then you can see that this max is going to return the maximum of the two values, right? So if x is less than y, then the bigger number is y, Therefore, it's going to return y. If x is not less than y, then x could be the bigger number, so it's going to return x. Okay, and then once you define a function, you can use it by typing in that function with arguments, and then it'll evaluate the function, and then it tells you, okay, so the max of 2 comma 3 is 3. So any questions so far? Seems simple enough, right? So far? Okay, good. So we will we are just going to learn just one more construct before getting into more complex functions. So sometimes, you want to do, instead of writing a very complex expression, you want to break it down into a series of steps. And for that, you use what is called a let statement in standard ML. So for instance, you can say fun f of x comma y is, I'm going to define 2 intermediate expressions, and then I'm going to say it's x2 plus y2, right? So this is, the meaning is exactly the same as, fun right? So this is the meaning. It's just that instead of writing one long expression like this, we have broken it up into smaller sub-expressions. And of course, this expression is not so complex, and is not worth breaking it into pieces like this. But when you write something more involved, you will definitely see the need to break down a complex expression into smaller pieces. Okay, and lets can be used to define values or functions, right? So for instance, you can define a function f of x comma y, and in that function, you may want to define another local function called sq of z equals z times z. And once again, you can understand this in the same way. You can right? So this is still exactly the same function, but the way you have, made it, broken this expression is by defining a function for computing the square and then using that function on each of x and y, right? It's just a different way of breaking things down. Neither of these decompositions is particularly helpful, but all I'm trying to do here is to illustrate the let statement so that when you do have something complex, you can break it down into smaller pieces like this. Any questions? So, and then the last piece is how you print. So standard ML has a built-in function called print. And if you just type print, it tells you, hey, that's the name of a function which takes a string argument and produces nothing, right? So unit is a special type, okay, which stands for essentially nothing, right? So you can think of it as the empty set, because there is no output that's produced, okay? So a print function is going to take a string as an argument, and it's not going to return anything, right? That's what it says, unit, right? Of course, it's going to print on the screen, but that's not the same thing as having a value, right? So in this case, for instance, if you call f of 2 comma 3, then you will get a value 13 printed, right? So f has a value that is 13, whereas if you print, yes, you will see what you print, but it is not the value that's being returned by the print function. Okay, the print function returns nothing. So one thing to remember is that print only prints strings, right? It doesn't know how to print integers or real numbers. So it knows only to print strings. So if you want to print an integer, then you have to use a support function like this. So now you see something that seems much longer than what you have seen so far, but it's basically a function called toString and in a module called int. Okay, so the library functions available in standard ML are organized into what are called modules, and this is a module that contains a bunch of operations relating to integers. And one of those operations is a toString operation, which converts an integer to a string. So if you want to print, you cannot print an integer directly. You have to first convert it into a string, and then you may want to sort of print it in together with a few other things. So that's why you are taking this string, concatenating it. So this operator, right, the caret operator, is a concatenation operator. So you're concatenating the string with this integer, and then ultimately you're also concatenating it with a new line character, so that after printing it goes to the next line, right? So when you do that, it'll print something like this, right? I know 10 times 20 is 200, and then it goes to the next line, and now it prints the value that's returned by print, which is nothing, right? And so that's what it says. Okay, a nothing value is denoted by a pair of empty parentheses like this. Okay. So let me conclude by just showing a few recursive functions. So here is our Fibonacci, right? So if you type this in, then it's going to that's the definition of the Fibonacci series, right? So if you type this in as a function into standard ML, it's going, and then you can say, hey, g of 3, and then it'll print the third Fibonacci or fourth Fibonacci number, actually, right? So so why don't I stop here? What I would like you to do is I would like you to install standard ML on your machine, or if you run into too much trouble, at least use the web system and try out all the expressions that and functions we looked at in the class today, including this set, okay? And we will pick it up from there. Again, I don't think it'll take you more than 45 minutes to do all of this, right? So try doing this so that you will be in a better position to understand what we are going to cover in the next lecture, right? So what I'm going to do in the next lecture is, we are going to get a little bit more into programming in standard ML, looking at more recursive functions, and then beginning to write some non-trivial programs, right? So these are trivial programs, right? So you can see there are two lines. One is defining a factorial. No, it's not defining a factorial. I guess it's defining something like a power. But these are pretty straightforward things to define, and we will get a little bit more, complex programs in the next lecture. So let us stop here, and your TAs will be taking your recitation today. So join them around 4:30 or 4:35 whenever they start. So if you have any more questions, I'll answer them. Otherwise, feel free to hang up and take a break and go to your recitation.
If we wanted to learn an actual functional programming language for like modern use, would you still recommend something like OCaml, or some other alternatives like Haskell or something?
So Haskell is what is called a lazy functional programming language, and it
Mhm.
is somewhat of a different beast than standard ML, and it is also quite a bit more complex.
Mhm.
So it's I kind of think of it like C++, and I don't want people to, start working on C++ unless they have worked with several other languages before, because it's just too complex. And
Okay.
so Haskell maybe it does have many more modern features. It's an overall a better language and better system, but I would not recommend that until you have done some amount of functional programming. And the other
Okay.
thing that I want to tell you is that you can do a good deal of functional programming in Python, right? So
Mhm.
Python is, you know, uh, Python is really popular among two groups. One group is people who always wanted to write functional programs, and then the other group is people who don't really want to program but want to, use what is already available.
Mhm.
So
Okay.
yeah, so that you can do that even there. And Scala is another functional language. So
Yeah.
there are just many choices. I personally use OCaml because I guess I've used it in the past, and yeah,
Okay.
very good. Thank you, and I'll see you on Thursday.